many advanced techniques have come, so people can just like that model that machine and then analyze and find out what the mainly frequencies and amplitudes. So the goal is here to present vibration basics, very less mathematical intense. Okay. With that said, I'm just giving an overview. Before we jump into vibration topics, you should know the distinction between static and dynamic design. So I will give a little overview and then move on to vibration basics and some of the mathematical representation of vibration, single and multi-degree of freedom systems, which are very, very important to understand the vibration characteristics, and also the damping, which is very, very important. Damping plays a big role checking or reducing vibration levels and various damping mechanisms. Then what are the methods to minimize vibration in machines? With that, I conclude this lecture. Okay, and yeah, you can stop me. The mechanism you are following, that's fine. If you want to hold your questions at the end, that is also okay with me. But if you have any questions, you can stop and ask me. But I don't know. I don't see any chat here. Maybe if I get out of this mode, then I may be able to see. So can I do that, sir? Can I move out of this mode and present?
Yes, you can proceed, sir.
Yeah, so that I can see some, hopefully. Yeah,
Sir,
it's all.
Sir, we can have a question answer at the end.
The end, okay. Then in that case, it's fine.
Yes.
I have no problem. Okay, thank you, sir. Now, I will define what is statics and dynamics. Basically, statics is a subject that deals with the behavior of stationary part, basically, and under any applied load, steady applied load. It's just one load applied on the machine or a part or whatever. So, in that case, you design a part or a machine, and what you do actually is you calculate stress in that part, and you compare that stress with the material yield or ultimate strength. Okay, yeah, my part is well below the yield strength of the material or ultimate point, whatever, whichever you are comfortable with, you can compare with and say that, yeah, this machine is good. If the machine is very close to yield strength or yield point, then eventually it can get to yield point or ultimate at one point, and there are damages possible in your part. So the thumb rule is you have to be almost 50% away from the yield strength or ultimate strength. That's a guidance. That's all. And several situations may dictate that no, you have to increase that allowable limit. Then you can do it. And dynamics is a subject that deals with the behavior of the parts under dynamical conditions. Under dynamical conditions means the load is a fluctuating load. Okay, so in that case, the part will also fluctuate to the forcing function. So that's basically a vibration. Okay, so dynamics is part of vibration. Vibration measured under dynamical loads is used to evaluate the severity of the part. That means what is my vibration level? The level is okay, say A, and the worst is D, then it can cross B and C, then we are fine. But to begin with, if the vibration level is at D, then you have to do something, redesign the part and move that frequency and vibration levels. Okay, so the focus of discussion here is dynamics and its vibration basically. Okay, everything is okay so far?
Okay, sir.
Okay, okay, good. So basically what happens is in general bodies possess, as you know, mass and elasticity, and which is capable of oscillatory or back and forth motion, which is called vibration. Yeah, it could be any way. It could be a vertical motion or horizontal motion or axial motion, whatever it is, in either direction. In any vibration occurs, is a back and forth motion or oscillatory motion. Okay. Uh, as you know, vibration can have positive and negative effects. Like Dr. Subrato told this morning, it has good part and bad part. So I will talk about the bad part first. Uh, High vibration machine amplitudes are detrimental to machines. Okay, because if you reach the highest vibration level, then it will reduce the useful life because the fatigue life is expended already. Then, if you are originally designed for say 30 years, then it may not last 30 years. So it's very important. So you have to reduce the high vibration amplitudes. And it is also harmful for environment because a lot of noise. And we are all talking about reducing noise in the workplace and workshops as well. So it will be annoying, and also the noise if the plant is exterior, I mean in an open environment, it will be affecting all the human beings, animals, etc. Okay, so that's not good. So these are all bad vibration effects. So what is good vibration? So as you can see, if you want to sort out some dissimilar materials, you can use vibration theory. Vibrate the see whatever, and then it will separate two different materials. So it's good thing. And also music, acoustic vibration. That's basically acoustic vibration. It can form pleasant musical sound, uh, and it is very pleasant to listen and enjoy. Okay. So therefore, it's very important to learn in-depth vibration characteristics in order to solve the problem. Another thing I want to point out here is now for people who own pets, dogs, cats, and things like that, they want to leave it in the yard and they don't want to supervise constantly. In that case, you can also apply vibration theory. You can create a fence with high vibration surroundings. So the dog or cat cannot go to the periphery. So it will stay within that periphery. So that's also good vibration. Okay. Um, Now I want to get into mathematical description of vibration. As you can see in the left picture, a point in B with radius A travels along the circle. Okay, so if you plot the projection of B along the vertical axis, and what you see is a sinusoidal curve, very regular, and it just goes from 0, 90, 180, 270, 360. Okay, so it is a sinusoidal curve. So positive peak, negative peak, and you also can see that one cycle is one period. Okay, so if you know the period, okay, this many seconds or this many minutes, whatever it may be, then you can understand, okay, this period repeats regularly on a all circumstances. So the machine is vibrating at a constant period. That means it's a steady state vibration. Okay. So by knowing the period, you can also calculate frequencies, which I'm going to show here. The frequency can be measured or calculated uh, in the time interval, using the time interval. So if you have the period 1 over t is your frequency. Okay. So omega is a rotating frequency. Like just I show it. Yeah, this is the rotating frequency here around this. Okay. And we are equating rotating frequency to another frequency. It's called natural frequency, 2 pi f. If you know the period, you can calculate frequency as well. Okay. So in general, omega and phi, they're all interdependent. Okay. It's not separate. Whenever omega reaches a peak or a highest vibration amplitude, then that omega becomes f. It's just uh, it's a terminology used in the vibration subject. Okay. So from equation 1, you can, it's a linear amplitude. X is a sine omega t, and you can differentiate once, get the linear velocity x dot, and differentiate the velocity twice, then you get linear acceleration, as you can see here. And if you apply the x a sine omega t into it, then x double dot, that acceleration is nothing but minus omega square and the maximum amplitude. Okay. And so that's what we know what causes vibration, what's the frequency. It's all single frequency. So in order to define vibration, you have to know what frequency it is vibrating, what is the amplitude, what is the phase angle. Okay. All those things you should know. Okay. Otherwise, no, you cannot explain to an expert or talk to people, oh, this is my problem. Then the first thing they are going to ask is, what's the frequency? What is the operating frequency? Or if your frequency is far away from operating frequency, oh, no problem, you can operate. So that is the kind of thing. So as a vibration engineer, you should know these three parameters. Now moving on to the mathematical form, it can also be written in the complex algebra, like a sine omega t, I sine omega t. That's no two planar, the orthogonal plane. So you can write it as in the form of complex algebra. Okay. Now these are all the standard things. Okay. And sometimes the vibration doesn't occur a single frequency. So mostly it's involved multiple frequencies. Okay. So that's why it's called harmonic. All the frequencies vibrate at the same time, and it's harmonically related. Okay. So multi-frequency vibration can be shown as series of sines and cosines. They're all related harmonically. Okay. So this is the total form of the equation for a multiple frequency occurrence. So as you can see, the multiple frequencies. So you can see one here, single frequency, 1x. Okay. So one node at the center, and then you have 3x. It should be 3 nodes. So 1, 2, and 3. So 3 nodes. So it's 3x, 3 times vibration. Okay. And 6x and 8x, so on and so forth. So in general, the vibration you measure on a component is a combination of all harmonic components. Okay. So the resultant vibration signature is this. So that's the it is involved with all kinds of other modes. So, but the thing is, for one period, it, it it's a harmonic component. Then it can repeat exactly the same way to the other periods. Okay, that's why it's called harmonic motion. Okay. Now we can define vibration in a different way. One way is displacement, velocity, acceleration, and also you can calculate frequency using the period of vibration. Okay, 1 over T is your frequency. Okay, now the other way around is you can see that uh, this many, you are seeing two pictures here. One is with a heavy mass on the right, and the other one is a light mass. Okay, so heavy mass, light mass. The light mass with the same stiffness of the beam, K over M, the frequency is high. Okay, with the heavy mass K over M, so that will bring the frequency down. So that's why you see a few periodic vibration component here. Okay, so there are two ways you can define. Either you can define by a period 1 over T frequency, or you can calculate if you know the stiffness and mass. And when you design a component, you don't have these signatures available because you are designing the first time for the first time. In that case, what you know, the mass and stiffness. So as you can see, very simple, 1 degree of freedom system, mass and stiffness here is represented by a spring. So you can write the equations of motion in general, m y double dot, k is the stiffness of the beam, mass is the mass, and you can resolve this equation and calculate the frequency, rotational frequency or natural frequency. Okay, this rotational frequency become natural frequency whenever the vibration or the response reaches maximum value. So the other way of defining the frequency is, if you know the stiffness and mass, you can calculate. Again, I want to emphasize that this is applicable for very simple systems, and also you can calculate fundamental frequency only with this information. Okay. So the minimum required parameter to analyze vibration is basically mass and stiffness. And now we are moving to another parameter. Not only mass and stiffness, you should also know damping of the structure or system. Okay, so damping is another parameter which is used in the dynamical analysis, and most structures have material damping. Okay, any structure you take, it has got some damping, because when you ring the part, and it will vibrate for some time and then it will die down. Okay, that means there is some inherent damping in the system, which is called material damping. Okay, damping can take another form as well. Of course, material damping is hysteresis. You can get the hysteresis loop and calculate the material damping. And the second one is dry friction damping or Coulomb damping. So if two parts are what do you call, the moving against each other, depending upon the surface quality and the force, the Coulomb damping can change. Okay, so if it is a very smooth surface, it's almost zero, there is nothing. And if it is a hard surface, you will see some amount of damping there. Okay, and third is viscous damping. Mainly what I'm talking about is the oil film. So if you support a rotating part or a shaft on a bearing with oil film, the oil film damping is really tremendous. Okay, almost 70% of the damping is provided by the oil film to combat the vibration amplitude. Okay, so uh, that's why the turbine manufacturers, huge structures, they are all supported on fluid film bearings because they will give more damping, more um, what I call is also the capacity, the load bearing capacity. It provides really good. So as an example, I can give you, I know 500-ton rotor supported at two bearings, and it's only a 1 or 2 micron uh, thickness of the oil film, but that supports the entire load. In my experience in the shop, I went and rotated the rotor, which is 500 ton. You cannot even move it, and just rotated it just small way, easily within that oil film. So the oil film has a big effect in combating or reducing vibration. So damping plays a key role in the vibration, in suppressing vibration. Okay, only this happens at the natural frequency. So if you plot the rotation versus amplitude of any rotor or any structure, so you will see that there is a plot, but no, at all speeds, damping is not there. Then damping suppression is not there, or you won't see any damping effect. At the natural frequency, that's where it plays a key role in reducing vibration. Okay, at the peak can go up to any amplitude, but if we have a good amount of damping in the system, that peak will come down to a relatively low levels that is acceptable for you to run the machine. Okay, so that's why damping is very important. And now I'm just adding another parameter in the equations of motion, which we have seen before, mx double dot plus kx. That's what the mass and stiffness of the part. Now we are adding damping as well, cx dot. It's basically velocity driven. Okay. The solution of this equation is two parts. Okay, you have a oscillatory part and then constant part that's within the parenthesis. So the oscillatory part, which has got exponentially decaying function of the time, as you can see, e to the power of minus c 2m is mass damping and time. Okay, with the time, it will vanish. The vibration will vanish or reduce to zero or to a level, whatever level is acceptable to you. Okay, it's a low level. So as you can see, this is exponentially decaying term. That's what this one is, and this combined with the other constant terms will define the amplitude. Okay. So various damping behaviors. Using this term, you can apply all the parameters, mass, stiffness, and damping, whatever, and that gives you some idea about, okay, well, what is the kind of damping I have, whether it's over damped or it's under damped or it's critically damped. What is it? So that's what I'm plotting here, the displacement versus time. As you can see, the solid line here, it's consistently the same amplitude is sustainable. The vibration is sustainable. The same amplitude is not reduced. Basically it's a machine part. It has to reduce. But you see another one, the dotted line, that trend, that vibration trend is basically diminishing. So it will eventually go to zero or at a low level. Okay, whereas the overdamped system has no oscillatory component at all. Please carefully observe this. Only oscillatory components can cause vibration. If it is over damped, you don't have vibration. That's just some line, uh, standard line. It's not a vibratory. Yeah, that's what I would say. It's not oscillatory, it's not vibratory. The same thing with critically damped system. You don't have an oscillatory or a vibratory nature. Okay, so these are the things you should know. But the one thing we encounter in our design or in reality is the underdamped system. Okay, how well it can reduce the amplitude, that's the thing we are interested here. So the damping, we should know how to measure damping, okay? Because in order to use it in your equations of motion and then find out what's my amplitude, what's my frequency and all those things. Of course, frequency is not dependent on damping, as you know. It's mainly dependent on mass and stiffness. That's what it is. But damping could help reduce the amplitude. That's all it does. Okay. So here is a signature I'm showing. The vibration signature. The amplitude is x1. The next amplitude is x2, x3, x4, something like that. So the logarithmic decrement is defined as natural logarithm of two subsequent amplitudes. Okay, that's the logarithmic decrement, and it can also be approximately equated to 2 pi zeta, which is a damping constant. Okay, damping ratio. So the other way of defining damping, usually this is done in a rotating machinery. So if you plot the displacement versus the rotating speed here, okay, or frequency, you will see that in the beginning everything will be almost nothing, no amplitude at all. But when the response reaches a frequency, you will see that the amplitude slowly increases and reaches its maximum value and then reduces back. Okay, so if you take this signature, the vibration signature, and then identify, okay, this is my maximum amplitude at which the frequency is critical frequency. Okay, and then you take 70%, draw a line at 70% of the maximum amplitude, and it will cut at 2 points in the curve. So drop those 2 points, then you have two sideband frequencies, F1 and F2. Okay, so the Q factor is defined as FC, the central frequency or the natural frequency or a critical speed. I'll talk about it later. Divided by the difference between two frequencies, okay, F2 minus F1. So this is called Q factor, and this is well known in the industry. People use this Q factor in order to balance the rotating systems and also to analyze. This is basically came from electrical circuit theory, okay, but it is useful information for mechanical systems. So it plays an important role at resonance only by limiting vibration amplitude, as I told you before. So damping helps to suppress the vibration at the natural frequency. So it is called Q factor here. Okay. Now let us let us uh, let us see how we can suppress vibration using the damper. Okay, so you can add a damper and reduce the vibration, which is basically you, vibration absorber. That's called vibration absorber. It reduces the amplitude, and sometimes you may not be able to absorb or reduce the vibration using the damper. Okay, so in that case you have to find out another way of controlling this amplitude or controlling the situation. So in that case, you can also design a vibration isolator. Okay, isolator in the sense it will isolate frequencies away from the operating frequency. That way, your natural frequency will be away from the operating frequency, and there is no vibration at all. Okay, so the vibration absorber. This is basically the picture shows that the absorber, which can be seen in automobiles, the shock absorbers placed in front and rear axles, and that helps absorbing the vibrational energy. Okay, so that is an example of absorber. Okay, and that will suppress the vibration amplitude, but it's still the frequency will be there, but the amplitude will be less. Okay, and moving on to the next one, vibration isolator. You may not be able to use this absorber all the time to reduce vibration. Sometimes it will reduce the vibration a little bit, but not to the extent that you want to reduce. Okay, so in that case, isolators are designed. Basically, isolator is another subsystem. For example, you have a main system, mass and stiffness here. That's the main system. Then you attach a subsystem with mass 2 and stiffness K2. So the, the whole system will behave in a different form. Like I show it here. You see the central frequency is supposed to be here, maximum. Now it's split by 2, 80% on one side and another 25% on the other side. So your operating zone is free with no vibration at all. So this is the kind of mechanism used in some cases as vibration isolator. So this needs a lot of experience, design, a lot of calculations to make sure that yes, my vibration has moved from the central frequency to other frequency. It's split. Basically, it's split frequencies. Okay, so this is also another way you can reduce the vibration. Okay. Now I will just talk about what are the conclusions based on what we have discussed so far. So a body with mass and elasticity is capable of vibration. Okay, it's all well known. Um, it could be a single frequency vibration or a multi-frequency vibration which is harmonically related. Okay, sometimes we will call it a periodic motions. Okay, and transient motions could be periodic or non-periodic. A transient is basically time-dependent motions. It could be periodic in the sense that they have same period at all times, or non-periodic. Non-periodic, we are not interested here because our, in general, systems don't behave that way, and if they behave, then it needs a different treatment. Sorry. So with the linear vibration theory, you can tackle periodic vibrations. Okay, so most systems we see in life is linear. Non-linear is non-existent because non-linear nobody understands. It's very difficult. You can create theories and it's only specific for particular instant or particular circumstances, and also not sure. People are not debating each other. Okay, this may be this, that. So I'm not going into that part of the world. So just linear. Linear is simple. Damping limits vibration amplitudes only at the natural frequency. So we have learned damping ratio logarithmic decrement, Q factor. These are the three parameters measured for damping. Now let's move on to modeling. Okay, so this is a very simple cantilever beam, as you can see. The one end is fixed, other end is free. This beam can be modeled as 1 degree of freedom, mass and stiffness. Okay, with this model you can only estimate the fundamental mode. See, this is the fundamental mode associated with the frequency. Okay, each mode has a frequency, is unique and specific frequency. Okay, that's the fundamental frequency. First frequency, sometimes it may be called, and second frequency is this, because it has got two node points, and the fundamental frequency is only one node point, and the third frequency, which has got three node points, 1, 2, and 3. Okay, three node points. So third frequency, but we are interested in the fundamental frequency. A simple cantilever beam can be modeled using mass and stiffness for obtaining the fundamental frequency. You cannot calculate any other frequencies with the simple model because it's very complicated. Okay, so 1 degree of freedom can be used, and one frequency can be calculated. So I want to just show the similarities of the structure and the human body. I'm using this cantilever beam theory. Is the bottom girl who's posing the yoga posture is not the same, exact same boundary conditions, but the curve is very similar to cantilever beam. So if you use these similarities, you can find out that this posture is highly energetic and most flexible of all your exercises you can do. So if the human body bent in this shape, the first mode of the cantilever has highest energy and more flexibility. It strengthens muscle groups, toes, legs, organs in the stomach, hip areas, and thyroid glands, because she is just bending her neck. Okay. Okay. Now moving on to what are the other machine elements that are common in the industry. So all rotating machines, automobiles, motors, pumps, and can be used in processing plants like paper mills and sugar industries, and steam gas turbines, small, medium, and large, and generators. They are connected to steam or gas turbines or both. Okay, sometimes they do cogeneration, so they can connect all of them: steam, gas turbine, and generator. Okay, all these machines above are called, they fall under rotating machinery. Okay, that's what it is. Any part, assembly, or substructure can be simulated using mathematical models. Okay, that's the part of it. In order to analyze vibration characteristics or studies you want to make, so you can do that by modeling. Okay, one simple model I want to show here. This is basically an automobile body. Okay, body is modeled, and then it's supported in the axial springs, and then in turn it is supported by the tires. So that's also has mass and stiffness. So if you have this kind of modeling, if you know the weight and stiffness of all elements, you can decently calculate fundamental frequency. Again, only one frequency you can calculate. You cannot calculate other frequencies, because the automobile excites frequencies, but you cannot be able to study with the simple model. Okay, that's why it needs different treatment in order to get all frequencies. Okay. So with one mass and spring model, we have seen that only fundamental frequency, it's called fundamental frequency, can be evaluated, and multiple frequencies can be computed with multi-mass, multi-stiffness models. So you have to do this many masses, whatever, so 10, 20 or 100, something like that, you have to do it in order to get all the frequencies. So the modeling of machine elements, you can, you know that it's a multi-mass. In that case, we have to use the modern methodology such as finite element methods, okay, in order to get all the frequencies and associated mode shapes. So if you need to get all the frequencies, the associated mode shapes also, in order to understand what's happening to the system, because you have node points in the mode. So if some critical component falls under the node points, so you need to understand that and then alter that with a design, with a redesign effort, okay? And medium and large structures in general can be analyzed accurately using FEM, but yeah, FEM is not the only tool. You should understand what are these the constraints, support systems, and the subsystem. They are all should be articulated in the finite element model. So just knowing finite element modeling analysis, I don't think that no, you will be able to understand. But that is the way to go for future. Okay. So I'm just moving on to a more complicated structure. The Jeffcott rotor is a very simple rotor system in the rotating machinery world, and it's a Jeffcott rotor is a central disc rotor with an equal shaft length on two sides, and then the two ends are supported at the bearings, oil film bearings. Okay, here it's all oil film bearings, and I will go to the next slide, which will be very clear. Um, this is the model people use to study simple systems, and once you understand how the simple system operates and how it identifies the vibrational characteristics, then you can use it for multi-disc system, multi-disc, multi-shaft systems. Okay, here it's the bearings are all fluid film bearings, so they have a unique feature. I will talk to you about that next slide. So this is a rotor, basically is a 3 degree of freedom, okay, but only 2 degree of freedom we are using, one of the orthogonal planes, vertical and horizontal. Okay, y is vertical and z is horizontal plane, and the two rotations about the two planes, okay, two axes, I'm sorry, and x is the axis of the rotor. Okay, so this rotor is supported on fluid film bearings. So fluid film bearings have stiffness and damping, and it's not the best part of this fluid film bearing is it exhibits direct stiffness in one direction and direct stiffness in the orthogonal direction and the cross coupled stiffnesses. What do you mean by cross coupled stiffness? So if a rotor moves in one direction, it can also, you can also see response in the orthogonal direction. That's why it's called cross coupled term. Cross coupled z plane to with y. So y with z, something like that. Okay, and the same thing applies for the damping, fluid film damping. Okay, this fluid film damping is in turn supported on a pedestal. So the pedestal has, it's a structure, so it doesn't have oil film damping, etc. So the cross coupling. Only it has got the moment and the displacement. Okay, and then it has got the base, the foundation. Okay, foundation is there. In some cases, you can apply the damping through another form of fluid assisted systems, but in general, they are all pretty much zero. Okay, so you have stiffness, yeah, K, PY, and KPC. These are all non-existent. It's just for research purposes only. So rotor modeling, you have to do discretize rotor continuum, and then that's in I'm sorry, bending forces in Y and Z axis and rotations about Y and Z, that is phi and theta. Okay. Then in turn fluid film bearing modeling, this is added at the appropriate node, sorry, and it gives all the 8 dynamic coefficients, 4 stiffness, 4 damping. And bearing support pedestal model, it has got stiffness only in most cases. And the last one is the base concrete foundation. It is very, very solid. So it doesn't have any stiffness. It's rigid. It's considered as rigid. Okay. Yeah, that's all I have. So for further reading, I would recommend to use my book, Rotor and Structural Dynamics of Turbomachinery. It has got all the details, all the information required for vibration engineers. Okay. And at this moment, I will also present that the department can consider the following things. Can give accelerated vibration course for graduate class online if you are willing. Total, it will be about 10 lectures. Duration of each lecture is about 40 minutes. This I have given one time. And now it's more online. It makes sense to go this way. And I have given joint seminars combined by academia and industries on rotor vibration with practical examples. It's basically 3 or 5 day courses. It was successfully conducted at all industries, Westinghouse, Siemens, what do you call the GE and MHI and all those places. And in the academic environment, I have given BIT, Anna University, Harbin Institute of Technology, Harbin, University of Central Florida, Orlando, and other places as well in Canada and other places. The students' feedback were excellent, and we give e-certificates after the end of the course. So this is what it completes my presentation. So you're welcome to ask me questions.